This design gives you a complete in-depth information that how the FPGA HDMI works. This will eventually cover FPGA board HDMI circuitry information, Vivado pipeline design, SDK application writing, and running the design on the board. Keep watching this video. You might be familiar with the different versions of HDMI. You might want to follow this reference to get complete information. Out of several HDMI versions, this design will especially focus on HDMI 1.4 standard in order to interface with FPGA designs. For this purpose, I'm considering some popular FPGA evaluation development boards because the HDMI output of these boards is HDMI 1.4A standard. Finally, I'm going to use a standalone design approach. However, the same design can be used in the Xilinx Xilinx design approach with a few design modifications. For a complete demonstration, I will take ZedBoard design as a reference. You can check the link in the description to get a complete design overview. However, whichever FPGA boards use such a transmitter IC, this design is still valid except for a few things. After completing this design, you'll be able to develop an HDMI video output interface on your own in order to display video or image processing output. I have skipped the detailed Vivado pipeline design and SDK application development steps. However, you can follow the link in the description to get the complete steps. Similarly, I'm using a Vivado and a Vitis 2021.1, HDMI 1.4 in Xilinx FPGA boards. The Xilinx FPGA development boards implement the HDMI 1.4 standard using mostly analog devices HDMI ICs. These ICs are ADV7611 and ADV7511. If you notice, Xilinx FPGA boards mostly have HDMI output interfaces and ADV7511 HDMI ICs are already there. You must not get confused with the HDMI 2.0 and the HDMI 1.3. If you are thinking why Xilinx FPGA boards are using analog device ICs, well, this is because analog devices offers Linux drivers so that Xilinx customers can leverage the Xilinx Xilinx tool to develop Linux applications. ADV7511 HDMI transmitter IC. It supports a wide range of input and output formats. You can find the datasheet link in the description section. The IC is basically performing parallel to serial data conversion, meaning the IC receives the parallel video data from the FPGA logic as input and inputs them and outputs them as HDMI signal. The IC supports a wide variety of input formats. For example, the input data bit can be from as few as 8-bit to as many as 36-bit. It can have either separate sinks or embedded sinks. The separate sinks means the IC has distinct pins for sync signal input, so the input data and sync signals are separated from each other. On the other hand, the embedded sinks means the IC still has a pins for sync signals, but they are not used or mostly grounded. Therefore, the input data has a sync information embedded within the parallel data. This can be observed in the following pictures, highlighted by the blue colors. The table summarizes the various input formats supported by the HDMI IC. Whichever FPGA boards or any other devices use ADV7511 HDMI IC will have one of the above pin configuration. Let's see how HDMI IC is configured in the following boards. On these boards, the HDMI IC is configured with input ID 1, that is, YCBCR422 16-bit input with separate sync signals. This picture is clearly showing the detail pin configuration. These boards HDMI support 3 styles of input data with the right justification. It is highlighted in this picture. This information will also be needed while doing the register programming. Out of 36 bits, the bits from 8 to 23 are used for 16-bit parallel input data. To understand the above thing at the circuit level, let's look at the HDMI schematics. Let's identify the each signal as shown in this picture. Only the pins from 8 to 23 are used for 16-bit parallel YUV422 input data, and there is also HDMI clock, and these are highlighted in green color. Meanwhile, other pins highlighted in gray color are not available to use. There are separate sinks. These signals are highlighted by blue color in this picture. ADV7511 IC is the programmable IC. This is done by doing the IC register programming by I2C Communication protocol. In this image, the pins are highlighted in a yellow color. The HDMI output interface signals are highlighted in the red color. The signals go straight to the HDMI connector and are ready to be displayed on our HDMI monitor. Audio interface and interrupt. In most FPGA video designs, these signals are rarely used. HDMI transmitter on these boards is configured with input ID 0, that is RGB or YCBCR444 24-bit input with separate sync signals. Let's look at the schematic. The HDMI transmitter has similar signal as we discussed in the previous sections. Data line signals are highlighted in green color while separate sync signals are highlighted in blue color. Programming interface signals are highlighted in yellow color. HDMI output interface is highlighted by red color. Other interface signals are audio interface and HDMI interrupt signals. The HDMI transmitter IC is configured with input ID 0, that is RGB YCBCR444 36-bit input with separate sync signals. The HDMI transmitter has similar signal as we discussed in the previous sections. This picture shows the signal identification. In this section, we will cover Vivado pipeline design by utilizing the above information. This picture shows the general view of interfacing between FPGA and ADB7511 HDMI transmitter IC. Stream source. This represents the XC4 stream source, which can be the stream from HDMI input, media devices, memory buffers, or test pattern generator IP. In most cases, in the early stage of video pipeline design, Xilinx video test pattern generator or BTPG IP is mostly used. If the source has an RGB stream, it has to be converted into YOV422 or YOV444 color format. If the source is directly able to give YOV422 or YOV444, then obviously the color conversion won't be necessary. Video timing. It includes the generation of video-related information parameters such as synchronization pulses, polarity, blanking period, active video signals, etc. This is shown in this picture. It is required to synchronize the processes and control the video data. Xilinx video timing controller, that is PTC IP, can be used to generate video timing signals. Access to video out IP. The XC4 stream conversion into native video formats takes place here by the Xilinx XC4 stream to video out IP. This IP utilizes the video timing information as well as streams to convert video data into displayable video format. The IP has one of the customization options to set desired output video color formats such as RGB or different YOV formats. In most cases, the parallel data with it set according to the color format selected. Custom logic or IP. If the ADB7511 HDMI transmitter IC is done with embedded sync configuration, the access to video out IP's output signal, that is parallel data and sync signals, will be required to convert and generate final parallel data output with embedded syncs. I2C. Xilinx XC I2C IP plays a major role in implementing the I2C communication protocol in order to program the HDMI transmitter IC. Clock generator. This is necessary for our design to get the required clock signals to drive the entire FPGA pipeline, including the media clock. Xilinx clocking wizard IP is most popularly used in such case. Zinc PS or microblaze. This forms the processing system of the design, where the application will be loaded and run to control and configure the processing system itself, board peripherals, and pipelines in the programmable logic. Finally, when we acknowledge the above pipeline design flow, we get the Vivado pipeline design as shown. This represents the base level design for ZedBoard, JC706, JC702 boards. This represents the base level design for SP701, AC701, KC705, and VC707 FPGA boards. The pipeline is designed to generate the 1080p at 60 Hz video output, which will be fed to ADB7511 IC to get HDMI output to display on the HDMI monitor. Okay, constraints. Without constraint, the signal will never be able to come out from the FPGA chip. Whenever the designs have floated pins or the ports, the constraint mapping must be done. While manufacturing the FPGA boards, some of the FPGA physical pins are already soldered to some specific board peripherals. The constraint helps the FPGA design signal to be physically connected to those FPGA physical pins safely. That's why the FPGA development boards have the master constraint files. The blue highlighted pins are the actual FPGA physical pins, which are already soldered with the ADB7511 IC input signal pins. The red highlighted pins are the ports of our pipeline that we just created in the Vivado. And finally, the yellow highlighted constraint line is really important that you must not forget, because it sets the I/O standard for our ports. However, most master constraint files already have this constraint included, so you might not need to worry. You might have noticed that in this constraint description, the ZedBoard and SP701 has a dedicated I2C constraint, while other boards don't have I2C constraint information. So this is because these boards have onboard I2C switch to communicate various peripherals, including HDMI transmitter IC. Xilinx has mostly used Texas Instruments Semiconductor PCA-9548. This information will also be required while programming. This picture shows that the I2C switch used in these boards. The red highlights show the HDMI I2C path from FPGA. Okay, code. Once the design generation completes, we can move to SDK application development using Vitis ID. As we proceed with this, the following two things have to be done. So first is initialization and configuration of TPG to generate YUV422 or YUV444 video in 1080p resolution. XC I2C IP initialization and configuration to program the ADV7511 HDMI TX IC. Here we do the programming of various registers of HDMI IC according to IC programming guide. Check the description section. Here we also need to have the information of I2C path. For the case of the ZedBoard and SP701 board, we directly program the ADV7511 IC. For the case of other boards, we have to set up a complete I2C path from FPGA to IC. So for this, we have to program the I2C switch to open HDMI I2C channel and then program the ADV7511 IC. This shows the quick information on register programming that should be done at least. So it is important that the first two registers, which are programmed according to ADV7511 input data configuration. Okay, here we program the 0x15. So we write here 1. This is for input color format in YUV422 with separate sync. This is for ZedBoard KC705 and JC702. So in the case of other boards, register programming value is 0x0. So this is for setting the color format RGB or YUV444 with separate syncs. And similarly, so in the case of 0x16 register, we write B8. The upper 7 bits represents the output color format, okay, which is 422, and the bits 5 down to 4 represents the input color depth, that is 8 bits, and the bits 3 down to 2 represent the input video styles. Okay, this is only for ZedBoard, KC705 and JC702 FPGA boards. For the case of other boards, its value is programmed as this. So other register value can be set as shown here. So the following register programming is done to set the coefficient for color conversion from YOB to RGB. The value is set according to the value given in the table 56 and 57. Okay, this is taken from the ADV7511 programming guide. So currently it has been used table 56 register value. Finally, we covered these programming steps. It completes our SDK application development. We have to build and run the design on the board. When everything is set, we should get the following bars output as shown in this picture. This is what we get in the UART terminal. This represents the register programming verification, and all the register programmings are correct. This development flow is valid for all the above mentioned boards. So for the complete code reference and the output demonstration, I have used a ZedBoard. Okay, so you can check the following link to get a complete demonstration. This design presented you with the fundamental FPGA design to work with HDMI 1.4 standard by interfacing the ADV7511 HDMI TX IC. You can follow this design flow to work with other Xilinx or other vendors' FPGA boards that include ADV7511 HDMI transmitter IC. It can be integrated with the higher FPGA designs. In your custom design, you can replace the BTPG or the test pattern IP with the actual input source. This design uses a standalone design approach for the better startup. In the future design, I will bring up the design with the Linux approach, and we'll also discuss HDMI 2.0 and HDMI 2.1. I hope you like this. Do not forget to like, share, and subscribe.